We're going to talk about some basic concepts of machine learning, and we're also going to see our first model, the naive Bayes. And at the end, we're also going to discuss about some performance metric. So usually I think this lecture takes about 2 full hours, but I'm going to try to compress it as much as I can so that I don't take too much of your extra time. Okay, so yeah, last time, short recap, we discussed about the standard learning paradigms like supervised learning, unsupervised learning, and semi-supervised and reinforcement learning. So we also presented some examples, and also saw some examples with active learning and transfer learning. So we got an idea of what a learning problem is, some concrete examples of learning problems. So in the lectures we will focus mainly on supervised learning and unsupervised learning. So in supervised learning we have two canonical forms of problems, like the classification problem and the regression problem. And in in unsupervised learning we have again two canonical forms. One is clustering, which can also take a hierarchical form. So in this picture is just a partitioning of the data set, which is flat clustering, but we can also have a hierarchical clustering. And we also have another task called dimensionality reduction. This is just to reduce the points to a lower dimension. Okay, so once we have this data fixed, we also discussed about the supervised learning paradigm, which is about having some training data. So these are some discrete examples from some continuous space X. And what we want to do through learning is to estimate this function with a function that is able to take as input a data sample X and produce the output Y. Okay, so another important aspect, and we're going to discuss more about this today, is that so we want to estimate this function on the training data, but in the end we will evaluate it on data that was never seen during learning. So this is to make sure that the learning algorithm doesn't cheat. So for example, a very simple a way to predict the precise labels on the training data would be just to store the examples, like, I don't know, in a hash table. So once you get your function gets an example that it has seen before, it can immediately reproduce the label. So this would be the extreme case of doing 100% on the training data, but on the test data, the method, of course, will not output any result because it will see new examples that are not in the hash table. So this is not learning. This is not what we want to do in the end. We want to be able to predict labels on new data. Okay, so the basic steps of supervised learning. So first, we have to set up a supervised learning problem. I think last time we really had a good example with face detection, in which we saw how we take this problem and formalize it as a binary classification problem so that we can apply a machine learning model on top of it. So first we need to design the problem so that we can apply machine learning models. Then we have to collect some data from our machine learning problem. So in this case, we have a training set of example, but of course we will need also data for testing the model. So data collection is one thing. So we have to collect, for example, some images or some audio files or some, I don't know, videos. So depends on the task that you want to address. And then you want to modify this data and for each data sample, so for example, for each image, you want to assign a vector from some Euclidean space r to the power of n. So this will be your representation of that image that you can use to apply a machine learning model on top of it. So the next step would be to choose the machine learning model. So this is about choosing actually a hypothesis class. So depending on the model, each model has a different hypothesis class. So for example, today we will discuss about naive Bayes. And the next step will be to learn, or actually to estimate some parameters of this model, which particularize it to a specific function. So the hypothesis class is just a class of functions that can map x to y, and then when you do the learning, you actually get one function that maps your data points x to y that minimizes your performance. So actually the performance evaluation is tightly coupled with the learning. So when you learn, you want to optimize some performance. So essentially this is the most important step, but not the only important step. Okay, so then we can see how the model behaves, and we can try to try different models, or actually we can turn back to any of the previous steps and try to readjust in order to obtain better performance. So we can also try to formulate the problem differently. Perhaps there is a better formulation that we can address our face detection task, for example, or perhaps we need to collect more data in order to obtain better results, or perhaps we need to use a better representation, and so on. So you actually can try to update any of these steps in order to gain performance. Okay, so one example about the hypothesis class. So actually this is to illustrate that choosing the hypothesis class is not that easy. So based on your hypothesis, you can make good or bad decisions. So this is just a toy example into words that are from two languages, which is banana language. This is the language spoken by minions, and we have here a set of samples. So these can be considered training data with the corresponding label. So we know that these are from banana language. Okay, and we also have a set of words from Furbish language, which is the language spoken by Furby. Okay, we have this data, and we can imagine, I don't know, try to imagine some hypothesis that okay, these words fall into banana language and these other words fall into Furbish. And then we get a test example, and we try to figure out if this test example belongs to banana and Furbish. And usually in class, if I would do this in front of you physically, I would ask you to vote, but now it's probably I'll fill the chat, so I will not ask you to vote. Anyway, so some of you, perhaps you can think of it, some will vote. Usually I think maybe half or something like that. People vote for banana or Furbish, and then yeah, this is the question. And I'm also trying to discuss about the hypothesis that they made. So for example, people may say, okay, we have a word that ends with O, and in Furbish we have different words that more words that end with O than in banana language. So it could be Furbish. But for example, in banana language, we have also a word that contains the bigram EL, and we also have here the bigram EL. So maybe it could also be a banana language. And actually, in order to get the ground truth answer for this one, you actually have to know that the hypothesis actually is more complex. You have to know that the words in banana language are actually borrowed from different or small adaptations from words that exist in different languages from Earth. So while Furbish is completely generated. So for example, in banana language, there are different words borrowed from Italian. So gelato is also a word in Italian, it means ice cream. So it is also borrowed in banana language. But this is a really hard hypothesis to figure out if you just look at this set of examples. Okay, so yeah, the main idea here, the takeaway is that learning is hard without establishing first a good hypothesis class. And now going back to the discussion of training versus testing. So in the end, what we want is to obtain good performance on training data. And actually, no, the right answer is to obtain good performance on unseen test data. So this is what I said before. Actually, the training data performance tells you something about how much the model learned, but it cannot be used as the only indicator. So if you just based on that, your model can make it can happen that the model have 100% accuracy on training data and predict random answers for your test data. So it's not the way to go. Okay, so yeah, given some training data, we just want to learn the mapping function on this training data, and then we want to evaluate it on new test data. So when we train the model, we don't have any labels for the test data, and we cannot make any, we cannot use this data to train the model. But actually in practice, you actually expect that you have some labels for the test data in order to compute the performance of the model. So you assume that during training you don't have any labels, but actually you need the labels in order to measure the performance. Okay, so this is how it works. Well, we also discussed about the how do we measure the performance. So we have different performance metrics. So for example, for regression problems, we can estimate the error using the mean absolute error, which just takes the absolute difference of the ground truth label and the prediction and sums up everything and computes an average. We can also take the mean squared loss, which just computes the difference between the prediction and the ground truth squared, and so on. So for classification, we have the misclassification error rate. So how many times you predicted the wrong labels. Yeah, and there are different metrics we are going to discuss more in detail today. So for binary classification, we can also discuss about specific metrics. And we're going to introduce these a bit later. And also, yeah, of course, the confusion matrix. Okay, so yeah, this is more about the practical performance metrics that we use, but in theory, we have the generalization error. So I'm saying in theory because this is a theoretical measure of error and is based on the integral on the on the whole space generated by the Cartesian product between x and y. So taking the integral over this whole space, so it means that it's computed over all the possible data samples in your space. So of course, in practice, this is not possible. You cannot have all the data samples. You can have try to have as many as you can get, but you cannot have all of them. So this error is actually measured on the is a theoretical error. So in practice, it is impossible to compute because the density of the space is impossible to compute. So then what we have in practice is the empirical error. So this is essentially based on the same formulation, but instead of integral, we use a sum. So this is a discrete version of this generalization error. So in the discrete version, we actually do a sum over all the data points that we have, for example, in the data set. Yeah, so yeah, this is an average over all these points. And this is a discrete value, and actually here the measure measure that we use, v, can be replaced with any function from the previous slide, which we're actually going to discuss later. So one quick question for you. So in the end, we want to estimate the empirical error on the training set or on on the test set. What do you think? This is a easy question, and I'm waiting to see the answers. Okay, have a live feedback here, and it seems that maybe you're okay. We have a good answer. Yeah, as I said before, so just proves that you're watching the slides. Thank you. So indeed, we want to report the error on the test set. So actually reporting the error on the training set is actually cheating. So it's not really fair, because you can go 100% easily. Anyway, so this is the empirical error, and this error is composed of different errors. So going back to the learning steps that we presented before, like representation, modeling, learning, and so on, actually all these components can introduce different errors in the model. So we have to distinguish between these errors. So assume that we have here the reality is the real function that we want to map. So there is a function f that maps the data x to the label y. In this case, the x is an image and the label y is a segmentation map. So it's the segmentation corresponding to this image, and we have some segments with the corresponding class. So yeah, this can also be viewed as a pixel level classification if you want. Anyway, so this is the reality, and this is actually a complex problem to model. So depending on your type of machine learning that you choose, you actually choose a hypothesis class. And depending on the complexity of the hypothesis class, you get what's called the modeling error. So the modeling error is, it gets smaller if you have a more complex model, and it gets larger if you use simpler models. And of course, this also depends if the reality is complex or not. So if you have a simple classification problem and use a simple hypothesis, of course, that's the best thing to do. You don't need a complex model. But anyway, there is this gap called the modeling error. So whatever you do during the learning of this model, you cannot get a better performance than this point. So this is the closest to the reality that you can navigate. Okay, then we also have the estimation error, which is caused by can be caused by the data. So you're working with some fixed data set, some discrete data set. It's not the complete data that you can have in your space. So then you just try to estimate this function on the data that you have, and you get this estimation error. And we also have the optimization error, which is caused by the learning step. So in training your model, you apply some optimization algorithm. We are going to discuss during our lectures about gradient descent. So this is one possible algorithm that you can apply. But for example, the algorithm for example, gradient descent can get stuck to some local minima, or it cannot optimize until the minimum point, because the gradient approaches zero when you're very close to the minimum. So there is some small optimization error, and people also work in trying to find better optimization algorithms for the machine learning model. So there is also the model, and also the learning that's important and can also be improved to minimize the optimization error. So actually, yeah, you have to think about learning, about data, and about your model in order to find the optimal error for you. Okay, so as I said before, the modeling error is caused by the hypothesis class that you choose. The estimation error is caused by the fact that you work with a discrete finite data set. And yeah, the optimization error is caused by the optimization algorithm. And there is also an error that we call the Bayes error. So actually, this is not covered here in this description is just that the Bayes error is again a theoretical error that you can achieve in theory, but and you can actually it is known and proven that you cannot achieve a better error rate than this Bayes error. But actually, in many cases, we don't know what's the value of the Bayes error. And in some cases, of course, it can be 0. So we cannot say much about the Bayes error. But you can imagine that, for example, yeah, it's like the maximum that you can get or you can expect from your algorithm. So of course, there are some edge cases, for example, that are very difficult to classify into one class or the other. And even for humans, for example, it is impossible to decide. Okay, so yeah, more on the Bayes error later. So now we're going to discuss about the bias-variance trade-off. So this is a concept that is known in machine learning, and this is actually related to the errors that I presented above. So these are related in what sense? It means that, for example, the bias is a systematic error that comes from the inability of the model to learn from the true relationship between features and labels. So this means underfitting. So this means that your model is not complex enough. So if you have a biased model, it means that the model is not complex enough. You need to expand your hypothesis class. And if you go to the other side, we have if we have high variance, then this is the random error that comes from the sensitivity to small fluctuations in the data. So the model, your model has enough capacity to learn everything about the training data, but maybe some of your training data, it's just it has some noise. So for example, images can also have some noise on top caused by the sensors that you use to capture photographs. So because of this noise, and the model if also learns these noise patterns and expects, so for example, if we see the letter 5 and the image has some noise, overfitting means that the model will expect that all the letter 5s will also have the same noise pattern, but that's of course not going to happen in practice. So each time you take another photograph, the noise pattern will be different. So this will not be correlated with the previous photos. So yeah, in this case, the model, if it does overfitting, it will also learn this noise pattern, and it's not right. In a test time, it will have a poor behavior. Okay, so this of course can be corrected by adding more data samples or by decreasing your model complexity. So if you add more data samples and your model sees more images of files with different noise patterns, it's going to learn that actually that noise is not so specific to the digit 5. It's more like something random that happens in the data set. So once you add more training examples, things start to become more clear. But anyway, so we have these types of errors that are they are linked like in this way. So this can also be expressed visually, this bias-variance trade-off. If you think that you're shooting, for example, on a target, and look at how the bullets hit the target. So ideally you want to have an optimal model, so not to have too much bias and not to have too much variance. So if your model has low bias and low variance, it means that your predictions are on target. If you have low variance and high bias, it means that okay, you're actually pointing in the wrong direction, but most of your estimations are clustered together in the same location. So here you have a high bias, but the variance is not that high. Then you can also have high variance and low bias. So means that you're actually also hitting on target, but you also have some some high variance, so you're also hitting you're also predicting some wrong labels here and there. And then, of course, the worst case is high bias and high variance. Well, also the model probably is not, I don't know, not learned properly, and it also has a small complexity. It will be in this case, but yeah, this is the worst case that can be. Okay, so this is also related to underfitting versus overfitting, and perhaps this is why I'm saying that is one of the most important problems of learning, because if you want to obtain the best performance on the test data, you will most often you will have to deal with this problem of underfitting and overfitting and find the optimal point. So yeah, in order to find the optimal point, so actually finding the optimal point is equivalent with improving the generalization capacity of your model. Okay, so the good thing is that if we have the training data and validation data or test data, we can empirically find this point. So if we have the performance error on this axis and the model complexity, if your model has the optimal complexity, it will hit this point. So this is also related to model complexity, but also related to the learning process. So you can start training the model. So for example, I'm talking about neural networks that can easily overfit to any data. But if you look at the error on training data and test data in the same time, and you plot them on a graph like this, you will notice that at some point, so they will start decreasing together. At some point, the test error will start to increase. So actually, this is the point where the model starts to overfit on the training data and starts to learn the noise in the training data, and which is no longer helping the model to generalize well. So once you notice this point, you can stop the training of your model, and if you want to achieve better performance on the test data, perhaps you can increase your model complexity or include more data and so on. So you can try other things, but the learning should stop around this point. Okay, so about the model complexity. So for example, if we have a very complex model and we want to model this data set of points, so this can be estimated with a curve, something like this. And if your model does overfitting, the curve will try to pass through each point. So the error here on the training, so imagine these are the training data. So your curve will pass through these points very close. But when you do, when you have a new test data, so you imagine you sample another set of points on top of this graph, the error will be quite high. So if you use instead of this, you use a less complex model. So for example, this is a smooth curve that has less parameters. Then you will probably get a better error rate. And in the underfitting case, you're just trying to fit this data, for example, with a very simple model like a constant function, which of course you can estimate the mean of these data points, but you will be your predictions will be very far away for some data points. Okay, and this can also happen in the classification task. So if your model is very complex, it will learn to classify all the data points correctly. So it will have a separating border that is very complex, has a lot of curvy shapes. And once again, if you imagine some new test data on top of this graph, probably this curve is not optimal. So, and this could be also, for example, outliers in your data. So it's better that during training, you actually learn this function, which is smoother. And when you sample a lot of points with the same distribution, you will get more correct answers than this very fine-tuned model. So this would be the optimal model, and once again in underfitting you're just trying to use a simple model that's not completely optimized, so it will not be able to predict even for obvious points. It will make wrong predictions. Okay, so yeah, this is about finding the optimum model. So next we will discuss about the different points of view. So for example, there is the procedural view. So in the procedural view, you just in the training stage, you just take your data and try to project it, or to extract some features from the data and obtain a feature vector. So this feature vector is actually a vector that represents, so there is one vector for each data sample in your training data, and this vector is from some Euclidean space R to the power of n. So yeah, one step here is to do the feature extraction, or to represent the data. So data representation or feature extraction is the same thing. Then you want to do the learning, so you get the data set X and the corresponding labels, and you want to obtain this function f through learning. And then in the testing stage, you have the raw data X, so this is this does feature extraction. So this step is identical to the step done in the training stage. So the algorithm or the procedure that you apply to do the feature extraction must be identical in the test stage, so it cannot be different. Okay, so for example, here if you want to represent, I don't know, images through, I don't know, color histograms, then here you also have to do the same and to obtain the histograms in identically the same way. So in the end, you will have similar vectors from the same space, and then you just apply the learn function f on top of your data in order to predict labels. Okay, so this was the procedural view. I'm shortly going back here. Yeah, I mentioned validation and test. I'm actually going to discuss about these quickly. Just wait, it will be in a few slides, okay? So it's going to become clear for you. Now I'd used it interchangeably, but actually you will see that it's not the case. Okay, so the statistical viewpoint, you can actually think of the data X and Y as some random variables. So so these are from some probability distribution that actually for us is unknown. So we have this probability distribution that samples, so these are just like random variables that can sample data for us, and we obtain the data set. Then we also suppose, in order to apply a machine learning model, we assume that the data is independently and identically distributed. And this applies both to the training data and test data. And well, actually, machine learning problems, if this doesn't hold, the standard machine learning problems need to be adapted for these cases. So, for example, you can I don't know, train the model or on some domain, for example, to classify, I don't know, objects, or to detect faces during daytime, so during pictures taken during the day. And then if in the test data, if you have pictures taken during the night, then your model is going to perform much worse. So you will not expect good performance. This is because the data will not be identically and independently distributed. So in order to make sure that to use the model in the same conditions as you used it in the training. So if you train the model on day images, your face detection model on day images, it will work okay on face detection on day images. But if it's trained on day images and you want to test it on night images, it will not work so well. So either you try to make some adjustment if you don't have training data with night images, try to adjust the model to the specific case, or just try to add data that has the same distribution as the test during training. Okay, so yeah, we do the learning on the test set, and then we have some hope that the model will generalize to the test set. So this is really, we don't have any theoretical guarantees that tells us that the model will work with the best possible performance. In the end, we have to try different models and see what works. Okay, so what are the important concepts to take away from the previous slides is the model capacity. So this is actually how large is your hypothesis class. Does it allow all the functions or not? What functions are allowed? Is your model only a linear model, or is it a more complex model, and so on? Another important concept is overfitting. We try to avoid it. So this overfitting happens when our model works well on the training data, but not so well on test data. So yeah, we want to avoid overfitting, and we want to improve the generalization capacity. So this is the ability of the model to achieve low error on new test data. So yeah, in the end, the guarantees are that yeah, if we have enough training data and if we have a good hypothesis class, then probably we can generalize to unseen data. Okay, so this ends a part of the first part of our lecture. We will discuss about a short recap about probabilities in order to introduce the naive Bayes model. So yeah, this is pretty simple. So we want to address the probability of an event. So if the event happens or not. So we have an event, and here let's say the event is Simona Halep will win Roland Garros. Actually, yeah, this can be posed for a question for the next year, and we are thinking, okay, what is the probability of this event to happen? So we have different views. So in statistics, what we do to estimate the probabilities is we assume that the event is sampled by some random variable. So we generate a lot of instances of this variable, and then just compute the number of times the event happens divided by the total number of samples that we generated. Well, of course, this is not applicable in this case, since we cannot make Simona Halep play Roland Garros to infinity in order to estimate a good probability. So yeah, then what we have, the next tool that we can use is the statistical view. So this is more about the belief of what we can say about A. And yeah, so we have the market design view, which will not discuss too much, is more related to the Bayesian view of the problem. Okay, so we're going to discuss more about these events, but before, yeah, just a quick recap of the axiom of probability. I'm not going to read them, I'm just going to maybe to explain the last one. So yeah, if we have the probability of two events, A or B, this is the probability of A plus the probability of B minus the probability of the intersection. So if we want two events to happen jointly, we have the probability in the intersection. So this is A and B. And we can compute the probability of A or B as the sum of the two probabilities minus the intersection, which is are actually added twice when we compute the sum. So we're going to use this graphical representation of the probabilities in order to explain the concepts, which I think is more easily to understand than just looking at math formulas. Okay, so yeah, if we sum up these areas, we actually sum up this intersection twice, well, so we have to subtract it in order to get the right answer. Okay, we also have conditional probabilities. So as the name implies, naive Bayes is about, actually, it involves the Bayes rule. So the Bayes rule involves conditional probabilities. So conditional probabilities, so for example, here we have what is the probability of event y having the value, so capital Y having the value y, given that the event, that the random variable x has the value small x. So we can also discuss in terms of random variables. Okay, so yeah, this can also be expressed as a Bayesian belief. So in our case, we want to know the probability of this event. So this is what we started with. What's the probability if that Simona Halep will win Roland Garros? Actually, yeah, here I have to update the slides and put 2021. And yeah, here we can also consider some events that actually can influence this probability. So this is the Bayesian view. To consider conditional probabilities, and instead of just looking at this individual event, we also look at related events. So, okay, what about if I tell you that in 2008, Simona Halep won Roland Garros, and she also played 2 other finals, but she lost the title then. Yeah, so I need to update this, but I'm not sure if she's on 6th place or actually higher right now, and so on. So in 2009 we had a different competitor that won, and now she was on the 1st place, and so I can tell you a bunch of these related events, and you can try to estimate this probability that Simona will win. Yeah, so this is a rough estimation, but still it gives you a better idea than just making a random guess, right? So I can say for sure that she has a better probability of playing or winning Roland Garros than I do, because I'll probably yeah, never get the chance. So of course, we have some conditional probabilities that we want to use. Okay, let's assume that here we have another example with conditional probabilities. So just to figure out the Bayes rule. So we have 2 events, have headache. So we have a headache, and another event, which is to have the flu. I'm sorry I didn't update the slides. Probably now I should add COVID instead of flu. So yeah, but anyway, so let's assume that the probabilities of these events is 1 divided by 10 and 1 divided by 40. And actually the conditional probability now is 1 divided by 2. So how is this computed? So we assume that f is a true event, so its probabilities, so this is the space of all probable events. So the probability of f is 1 times 40, so it's a small piece in this space. And so if this event happens, the question is, what's the probability of h, that h happens when f is true? So actually what we want to compute is this area that f intersects h divided by the value of this probability, the probability of f. So actually this is, yeah, the probability, the conditional probability, the formula of Bayes. So yeah, as you saw in the figure, we can estimate the conditional probability as the intersection of the two events divided by the event that happened. So this is the geometrical interpretation of the Bayes rule, and we can also express it like this. So there is also a mathematical proof that this is equal to this, but I think the easiest proof is again to think of areas. So yeah, if we have so the probability of B conditioned by A, it's actually the probability of the intersection divided by the probability of A. So if we want to express the same thing, we can also say that this is the probability of A conditioned by B. So this is actually the same area divided by B. So in order to obtain the probability of B conditioned by A, so we just have to multiply by this probability by the event B. Okay, and then we divide by the event A. So we have the same area, but is now divided by the other event. So we have the reverse result. Okay, so yeah, we're using likelihood. Some concepts in the Bayes rule. We're using likelihood. So how much does a certain hypothesis explain the data? About prior, so what do we believe before seeing the data? So for example, this could be the class distribution of the data. We know that, for example, in practice, if we collect many images of objects, we'll probably get many images of persons, because people usually take photos of people or other interesting objects. You will not see very often so many pictures, I don't know, of a common apple or something, or an object that's not really of interest. So yeah, there is some prior that you can estimate about the data, and then when you get the data, you also have some posterior estimation of this likelihood. So and also one interesting problem where we see the application of the Bayes rule. So I already took a lot of time, almost 1 hour, and I'm not sure if I'm at least halfway. I think I'm not. So I really need to make it quicker. Actually, we can try to also perhaps to stop earlier and see to continue next time. Anyway, so the Monty Hall problem, this is really interesting to do in class and to let people vote. But once again, you can think of what you would do in this situation. So the problem is you're in a television contest, and you have a big prize behind one of 3 doors, and yeah, you have to optimize your chance to win this prize. So essentially, the host shows you these 3 doors, and you have to make a choice. Of course, at the beginning, these are equally likely to, and you can make some choice. So for example, we pick a door. So for example, we opt for door number 1. Okay, so this is our choice. And then what happens is that the host opens one of the other 2 doors, revealing the goats. So there is a big prize, and the other 2 doors have 2 goats. So if you don't win the prize, you go home with a goat. And yeah, we are offered the option to change our pick. So we initially pick door number 1, then what happens is that the host reveals door number 3, and then the question is, do we switch to door number 2, or we keep our initial decision, door number 1? So many of you probably already know the problem and already know the right answer, but you will also see the proof now. So yeah, our options is to keep the initial choice, or to switch to to door number 2. So this is if we think that we improve our chances by keeping the door, we improve it by switching the door, or actually they still have equal chances and it doesn't matter. So modeling this problem with the Bayes hypothesis, so it's about knowing the a priori information. So this is assume that we have the hypothesis the price is behind door number I. So this is the hypothesis. So a priori we're thinking that all three doors are equally likely to hide the price. So it means that each gets a probability of 1 divided by 3. So we choose door number 1. So this, I'm retaking the steps here. So if the price would be behind door number 1, then the host is indifferent and can choose between doors 2 and 3 with equal probability. So here we're introducing the conditional probabilities. So yeah, if we know that the price is actually behind door number 1, then yeah, the probability that the price is behind this is the probability that the host will open door number 2 is 1, so they are equally likely, so the host can open either door number 2 or door number 3, so they have equal probability. So now the second case is if the price is behind door number 2. So then the host must choose door number 3. So it must choose the door that has the code behind, not the one with the price, right? So now it has a bias. So yeah, if the price is behind door number 2, he will not open door number 2. He will open only door number 3. And the same happens. So if the price is behind door number 3, then he must choose door number 2. So this is written in parentheses. So the vice versa happens. So if the hypothesis the price is here, he will definitely open this door and it will not open the door with the price. Okay, so yeah, this is the post the post probabilities. So now what happens, so the observation is that the host opens door number 3. So now the question for us is the price behind door number 1 or door number 2. So now we have these probabilities computed on the previous slide. So in order to find out where the price is, we just apply the Bayes rule now. So we assume we apply yeah, so what we want to find out, what's the probability? So we have only two options, so only two probabilities to compute. So we want to find out if the price is behind door number 1, given that the host opened door number 3. And using the Bayes rule, so this is equivalent to the reversed conditional probability multiplied with the probability that the price is behind door number 1 divided by the probability that the host opened door number 3. So if we look for these probabilities here, it's 1 divided by 2 multiplied by 1 divided by 3, so it's this one. And here actually if the host opens door number 3, the probability of choosing this door is 1 divided by 2. So he has only two door options. So in the end, this probability is 1 divided by 3. And we do the same computation for the other case, for door number 2. And we obtain the probability 2 divided by 3. So in the end, yeah, we have 1 divided by 3 and 2 divided by 3. Okay, so we have these two probabilities. And actually, we learned that if we choose door number 2, we double our chances of winning the prize. So in the end, the right answer is to switch and go for door number 2 in order to increase our chance of winning the prize. So we obtain this result by applying the Bayes rule. So moving on towards the naive Bayes classifier, we actually start with optimal classifier. So the optimal classifier is actually based on this probability theory. So we have a function here, it's denoted by h, that maps the data samples, actually the space x to y. So this is the continuous function that we want to learn. And supposing that we know this probability for the entire space, the conditional probability that given a sample x, we have this label. So if we have this probability, which of course in practice is impossible to obtain, we have the optimal classifier, which gives us just choose the class label with the highest probability. So if we have the probabilities for every possible data sample, we just consider the probability for all classes and choose the class with the highest probability. So that's simple, that's natural. The only problem is in practice we do not have this probability on the continuous space. So it's not possible to obtain it. So yeah, this is the optimal classifier. And why is it optimal? Because it's based on a theorem that says that this classifier is optimal. So this is called the Bayes classifier. Be careful, this is not the naive Bayes, this is the Bayes classifier. So it's a theoretical model. In practice, you cannot obtain it because it works on a continuous space and we're working with discrete data. And yeah, it is proven by this theorem that the error of this classifier is smaller than the Bayes error. So it was smaller or equal. So yeah, this is the classifier that we want to use in practice, and we cannot because it's not possible. Yeah, and we have the Bayes error is the error given that given this probability, you will make a wrong prediction. So okay, so yeah, this is the optimal classifier. As I said, yeah, this is more like a rhetorical question. How hard is it to learn the optimal model? Well, it is mainly impossible. But what if we try to reduce the problem? So what about using categorical data? So categorical data means that the data samples are not in a continuous space. So the data sample X, they are just values from some category. So for example, your data has a feature that tells you it's like a, for example, binary. It has years or not. Another feature that tells you that it has the number of legs, like has 2 legs, 4 legs, or more, I don't know. Another feature that, I don't know, represents some other things, the number of eyes, I don't know. A feature, does it have fur or not? And so on. So you imagine these features in a feature vector, and this is what categorical data means. So assuming that we have these, of course, the space of possible values is much lower. So, for example, for does it have ears or not, it's only a binary decision to make. It's not a complete continuous axis to have values on. Okay, so yeah, but even in this case, it is very, very hard to learn the optimal classifier. Yeah, so these are some interesting questions. So how many parameters will this model have? So let's suppose that we have a class prior. So suppose that we have k classes, and we have the likelihood. So for a given a class, we know what X looks like. So X is, let's say it's composed of n binary features. So we are simplifying even more the problem. So we're not talking about categories. We're talking about the number of features, which is binary. So X is binary. So let's assume this simplified case. We have k classes and we have feature vectors with n binary features. And now the question is, how many parameters does the model have to learn in order to be able to answer this question? So actually the question is, think of the probability that we use in this optimal model. So it's the probability of, so given a data sample, we know the label, right? So in order to have this probability, we need all the possible data samples in order to have to fully define this probability, this conditional probability, right? So we need the full data samples in X. So yeah, given these constraints, suppose that X is a binary feature vector, so it contains only combinations of 0 and 1. What is the total number of parameters of the model? So actually, yeah. Okay, so the question is for you. I'm waiting for some answers here. Of course, I will not try to take too much of the time to wait for an answer, but I hope that I can get a good answer to that I can that I can score. Okay, I'm not sure how far behind are you, but yeah, that's not the number of models. So the idea is that 2 to the power of n times k. Yeah, I think that's a good answer. Yeah. So actually the model is very complex, so you need 2 to the power of n features. So now imagine that yeah, times k. That's the right answer. We have a good answer. So the main idea is that you need all possible combinations of feature vectors. So all the combinations of 0 and 1 are 2 to the power of n, and you also have to have these for all object classes to have probability. So essentially you would need at least one sample from each example to have probabilities. So this is a minimum set of samples to estimate some probabilities, but imagine that in practice this is also impossible to achieve. So we have reduced this optimal classifier to a very simple case, and still, so for example, if we imagine take a very simple data set like the MNIST data set, where we have images of around 30 by 30 pixels. So this means around 900 components, right? So the number of features, the number of parameters that you need to estimate are 2 to the number of 900. So this is the number of parameters, and in order to estimate these parameters, you would need more data samples, right? So yeah, that's a huge number of parameters even in this simple case, and in practice is simply impossible to obtain. And yeah, this is just to get an estimation on one of what's now considered the simplest machine learning problems, the MNIST dataset, but it's still difficult. So yeah, in the end, the model is very complex, and even if we try to apply it with limited data, it will have very high variance. So it's a very complex model. It needs a lot of parameters to estimate, and if we don't have enough data to estimate, we will get very high variance. So the model is complex, we have limited data, and it will not work. So the optimal classifier in practice does not work because we have limited data. and it needs to estimate a lot of parameters. Okay, so now we're going towards the naive Bayes model. So the naive Bayes model is based on some independence hypothesis. So yeah, we just assume, so let's say that the probability of x and y is equal to the probability of x times the probability of y. So this is true if the two variables are independent and identically distributed. So we can also extend this concept to conditionally independent probabilities. So the probability of x and y to happen given that z happened is the probability of x conditioned by z and probability of y conditioned by z. Okay, so we just multiply these probabilities, right? So what this means that instead of computing this, we can actually think as to replace actually x and y as the features that we are discussing previously. So for example, on the NIST dataset, instead of trying to combine the joint probability of some data samples that is represented by 900 features, now we just have to compute the probability for each feature independently. So this significantly reduces the number of parameters that we need to estimate. So yeah, this is the naive Bayes assumption. The assumption is based on a naive assumption that the features are independent given the class, right? So what we say is that instead of computing this probability, we just estimate it with this product of probabilities. And if indeed the features are independent, this is actually true. Of course, in practice, this doesn't really happen. So take, for example, the NIST dataset with images, right? So if you imagine every pixel in the image, of course, these are not independent. They are correlated. So for example, if you look at a black pixel in the image, it's most very likely that the pixel close to it, to the left or to the right or above, there is a very high probability that the pixel will also be black. And the same thing happens for white pixels, right? So only at the border these probabilities will not hold true, but mainly the pixels are correlated, so they are not really independent. And the same happens with the categorical features that I told you before. So of course, for example, if the feature has fur is true, it's probably going to have also four legs, or I don't know, something like that. So for example, for a marine animal, if has fur is so for a fish, right? If has fur is false, it also has the number of legs 0. So these are also correlated. They are not independent variables. So yeah, what I'm trying to say is that this supposition, this assumption is not true in practice, is almost always not true, but still we make this assumption, and the model, the naive Bayes model, works quite well even if the assumption is not met. Okay, so yeah, we have this probability. So this is for the two variable case. So in general, considering a feature vector with n dimensions, so we estimate this probability with the product of all the individual components. So yeah, I'm sorry. So this I should have hidden these results, so to let you give an answer. So but now the answer is written, so I cannot make the question anymore. But yeah, in the end, so if you take the same example as before with x that is composed of n binary features, then the number of parameters that you need to estimate now is 2 times n. So imagine that 2 times n in the previous case with MNIST will be 900. So in MNIST we can use the images with black and white pixels, for example. We can transform them into a linear vector, and then we have some binary features, and yeah, we can apply the naive-based models, and we only have to estimate 2 times 900. It means 1800 parameters. So this is the number of parameters. In the NIST dataset, we have tens of thousands of images, so we can easily estimate those parameters and apply the naive-based model. Okay, so yeah, the naive-based model is a model that we can use on discrete data. Yeah, so we have some class prior, the probability of classes. We have n conditionally independent features, and for each feature we have the likelihood given this feature, what is the probability of having a specific class. So we have this likelihood for every possible class, and then our decision is based on some adaptation of the optimal classifier, which is argmax of this probability. So we have the a priori knowledge, the class prior, and also the probability of the current data sample X, which is formed of n variables given that we have Y. So this actually can be obtained by replacing this through the independence assumption with the product of these probabilities. Okay, so this is the naive-based classifier. In practice, actually, there is a small note here. Is we replace this product of probabilities with a sum of logarithms. So you already see the question. Why do you think we do this? So it's a question for you. Why do we replace the product of probabilities with the sum of logarithms? Waiting for the answer here. It's faster. It's not about time. I think the time is about, I think, the same, or actually a bit worse. Yeah, we have a right answer. So yeah, it's because actually of estimation errors on the computer. So when we do this, imagine, so for example, we have here the MNIST dataset. Once again, we have 900 features, so we'll not need to multiply 900 numbers that are all below zero. So these are probabilities, and they are likely very small. So imagine if you multiply all these numbers, the computer will not be able to estimate the probability correctly. So in order to avoid these estimation issues, we use a sum of logarithms. So this is the answer. So if we use the sum, we just sum up these values. It's better than doing the product because the product will decrease the values more and more. Okay, so one important aspect here is if the assumption, the independence assumption holds, it means that the naive-based classifier is the optimal classifier. So, but as I said before, in most cases this does not happen. So, but anyway, naive-based works fine in practice, even if the assumption does not hold. So usually in order to estimate the parameters, we apply an algorithm called maximum likelihood estimation. This is actually just about estimating these probabilities through a statistical analysis of your training data. So in order to compute the probability X conditioned by Y, so these are the probabilities that you need to compute. So these probabilities here. So for each value of a feature, you need to compute the probability for the probability for all the possible classes. And yeah, this is also another thing here to mention. So even the naive-based model is not cannot be directly applied on data with continuous variables. So still we need to transform the data into categorical variables. So one option, if we have some continuous features, is just to divide the space between minus infinity and plus infinity into some bins. So for example, we can divide it into 4 bins, and for each bin we assign a number 1, 2, 3, or 4. So this becomes a categorical variable with only 4 possible values. So yeah, this is one thing that we do here. So assuming that the data is already in categorical form, we just compute these counts. So how many times a feature has a certain value and the respective data sample belongs to a certain class. So once we estimate these counts, we divide them by the number of possible the number of examples in the dataset, and we obtain some probability, and this is maximum likelihood estimation. So of course we also have to previously estimate the class priors. So what is the probability of the classes, and then yeah, we just apply naive Bayes and obtain the results. So yeah, usually I would have done a small exercise in class with you, but again I need answers from the class. And yeah, I actually ask people who plays football, who doesn't play football, so I have these answers. So I assume that the population is the entire class, and then who watches sport and who doesn't watch sport, and who is a girl and who is a boy. So these are my variables, and I'm trying to estimate the probability that you play or not play football based on these two variables. So yeah, we compute some probabilities, and then we take another data sample that is asked not to answer the question, and then we do some estimation. And yeah, this is a toy example. Actually, I think you also do a similar example in the lab. So yeah, I'm going to skip this part. Okay, so yeah, what I said before, that the naive Bayes assumption can be violated in practice, but it's not a problem. It still works. There are also often issues that the probabilities are biased towards 0 or 1, but still naive Bayes is popular, and it's used in probably many practical still used in many practical applications. So one of the examples in which it works very well is spam classification. So email classification into spam and not spam. Okay, so now going back to the underfitting versus overfitting of the data. So we're trying to address this problem. So splitting the data into training, validation, and test is a first important step. So this also answers a question from one of you guys. So yeah, we have the whole data set, and we have to split it usually in training, validation, and test. So in order to ensure a good generalization capacity, we have to test it on unseen data. So yeah, we can decide on some partition of the data set. So for example, we can keep 50% of the samples for training, 25 for validation, and 25 for test. So this can have various percentages. Usually we want to keep more training data to be able to train a better model. And of course the percentages can vary. So why is not enough just to split the data into training and test? Because actually when we want to think of the basic steps that we discussed about data representation, modeling, and learning. So you all will make all these adjustments on your, if you do it on your test set, if you look to increase performance by doing these adjustments and tweaks to your model, In the end, you will probably overfit the hyperparameters of your model to this data set, like the data representation or the regularization of the algorithm and so on. So there are different aspects that you can change to increase performance. And yeah, in the end, you will kind of wear out the test set. So in order to avoid this, we need a validation set, and we need to fine tune and to try to improve the model with respect to the validation set. And finally, once we have the final model, then we apply it on the test set. So it's not right to estimate or tune the model on the test set. So yeah, for your project, when we will release the data for you to work with, we will have some training data, some validation data that you can use. So actually the validation data, you will not get the labels, you will only get the labels for your training data, and the validation data will be a part of the private test set, and you will see the results during the competition on this validation data. So once the competition ends, you will be able to see the results on the actual test data and see your actual ranking. So if you're trying to make many model adjustments on the validation data, it might not be you might not go in the right direction. Okay, so yeah, the training process should look something like this. So you get some training data, then you split it randomly into test and training plus validation. So then you keep this data, the test data, untouched, and then you try to use this training and validation data to split it once more, and you get a training set and a validation set. And then you adjust your learning system, you train it, you evaluate it on the validation set, then you optimize your hyperparameters, trying to improve the performance on the validation set. So once you're done with this, then you can go, so you take the model with your final hyperparameters and you apply it on the test set and obtain the final error estimation. So this is the correct way to evaluate the model. And now you see that there is a difference between the test set and the validation set. Another way to work with this is to do cross-validation. So when you don't have enough training data so that you can split it into training and validation, you can use cross-validation to train your model, which is just splitting the model into k equal parts. And then you train the model on k minus 1 parts of the training data, and test it on the one that's left out, and you repeat this for a number of times and average the results. So this is the leave one out, and you can also do this. Sorry, this is the cross-validation procedure, and we also have the leave one out cross-validation procedure, in which the number of faults is equal to the number of data points. So this is another option. So yeah, we have the training data, we have a random split of this data into k folds, and then yeah, we split the data into first fold. We split the data into these folds and the first fold. So in the for the first fold, we train the model on these k minus 1 folds and evaluate it on this one. Then we move on to the next and train the model. So this is a different model with new weights, right? So we train it from scratch. So yeah, we use this data to train the model once again, and we evaluate it here. So we get different error estimates, and in the end we obtain an average of these error estimates. So once again, this should be done prior to evaluating on the test set. Yeah, other options here to improve the generalization capacity of the model. So one important thing is to split the data correctly into training, validation, and test, or to use cross-validation. And then you can also apply other concepts like early stopping. This is what I explained earlier on the graph. So early stopping means that you stop the training process once you see that the performance on the validation starts to increase. And another option is to include a regularization term. So when you optimize your model, you want to minimize some performance metric, and in the minimization problem, you also add another term, which is a regularization term. So this term ensures that your function doesn't have a complex shape. So actually, yeah, this is a kind of abstract concept right now, but we will discuss about regularization when we talk about kernel methods, and you will actually see what's the effect of the regularization parameter in ridge regression and in SVM. So you'll have some concrete examples right then, but right now just try to interpret here just abstractly like this. And also we have a parameter lambda that actually controls the importance of this term with respect to actually minimizing the error. So imagine if you use a very big lambda here, the optimization will try to focus to obtain a more regularized model. So it's a less complex model, a simple model, instead of optimizing the objective. So it's kind of a trade-off between the two, and you need to find the optimal trade-off. And it's also about the trade-off is also about finding the optimal complexity of the model, right? So if you don't use regularization, the model will overfit, can go to overfitting. So you'll just try to optimize this function to the maximum. If you use very high regularization, the model will not focus on this term and will just focus on building a simple model, which means that you will get an underfitting. An underfitted model. So yeah, it's kind of here you try to optimize by choosing the right regularization and by choosing this term. And actually in different models, this is renamed, I don't know, in for example, in support vector machines, we will discuss about them later. This parameter is called C. So we'll need to optimize that parameter in order to achieve the optimal training. Okay, so yeah, this is we also completed the second part of our presentation, and yeah, we still have a few more minutes, so I think we're going to finish in time. Yeah, so this is about model evaluation. Okay, so how do we evaluate a machine learning model? So first example is just to measure the accuracy on the error or the error on the test data. So it's important to measure it, I stress it out, on the test data and not on the training data. So in this example, we have some images with some labels. So 4 of these are correct and 1 is wrong. So the accuracy is 66%. And the error, we have 2 wrongly labeled examples, and the accuracy is, sorry, the error is 33%. Okay, so this is the error of the model, or the misclassification error rate, or the accuracy. So if we want to analyze this error more closely, we can use a confusion matrix. So confusion matrix gives us some more detailed information about the predictions of the model. So we have on the columns, we have the predicted labels, and on the rows, we have the actual labels. So this is the representation that I chosen. in practice, you can also have different representations, not necessarily this exact one. So it can be switch the two, but anyway. So here we have, for example, so if you do the sum of these, you get, it tells you that you have two examples that are from the class dog. And if you do the sum on the column, you get two examples are predicted as class dog. So here, if an example is has the actual label and the predicted label is correct, then it is it appears on the main diagonal of this matrix. Otherwise, so here we have, for example, an example that is this example is actually a car. So this is the actual label, but it was labeled as a dog. So this number here corresponds to this example. If we go to this example, it seems that we have a dog that was classified as a person. So we have this dog here is classified as a person, so it's wrongly labeled, it's put here. So what information we find from this confusion matrix is that the model might have some bias in classifying data samples into various classes. So I can go to, I don't know, to a more complex example. Yeah, so for example, let me have a quick I think I have on some paper a more complex confusion matrix. So in this paper, for example, we have let me just check that I have the confusion matrix before I start explaining stuff. Oh, sorry, no, okay, so I remember it's not this paper, I think it's this paper. Oh, come on. Okay. I don't find the paper with the confusion matrix. Maybe it was this one. No. Okay, yeah, I should have added probably in the slides some better example. Or wait a minute, I might have maybe this one. Yeah, we have some confusion matrices here. Okay, so we can look at these. So yeah, this is a more complex confusion matrix with which shows that, for example, okay, so just a brief context. So in this task, we had to classify essays written in English. So these were written for the test of English as a foreign language. So the TOEFL test, that's for students that want to study in the US. So they come from different countries. So the task is to identify the native language of the person that wrote the respective example. So here, for example, yeah, we have Chinese, Japanese, Korean, French, Italian, Spanish, German, Arabic, and Turkish. So we see, for example, here we have these two languages that are spoken in India. So it's Hindi and Telugu. So these two languages are more closely related, and we see that there are more confusions for these two related languages here. And yeah, so the confusion matrix gives you some more information about the things that, and you also look at as a general picture, you see that Chinese, Japanese, and Korean also have a bigger confusion. If you look, I don't know, the colors, here we have Japanese and Korean, we have bigger confusion here, and there are also some confusion in the Romance languages like French and Spanish and Italian and so on. So if you look, for example, with French and Indian, there is no confusion here. Anyway, so this is the main idea is that the confusion matrix gives you some additional information about the errors that your model is making, and you can try to improve your model by trying to address these specific errors. So for example, in this case, one idea would be, okay, this doesn't work so well, perhaps we need more examples from Hindi and Telugu to improve the model. Otherwise it works very well, but here we have a lot of confusion. Let's collect more samples. And here I think we evaluated different models, and we see that there are different. This one has more confusion, even more confusion in this case. So yeah, anyway, and also from the confusion matrix, you can also obtain the accuracy and the error of the model. So the accuracy is just the sum of the components on the main diagonal divided by all the components, and the error is the sum of the elements that are outside the main diagonal divided by the total number of components. And for the binary case, we can also compute the confusion matrix, and this has an interpretation. So we have the true positive rate, so the predicted as yes and actual yes. This is the true positive rate. We have the false negative rate, so if an example should be labeled in this case as a person and you do not label it as a person, you count it as a false negative, and so on. So yeah, here we have the number of true positives, so how many persons are actually labeled as person. We have these two people here. Then we also have a person that is not labeled as a person, so this is labeled 1. And we also have a false positive. We have this dog that is labeled wrongly as a person, and so on. So you get the confusion matrix in the binary case. And other metrics for this binary case are the precision. So this is computed with respect to the positive class. So what's the precision of the model on classifying person? So we compute it as the number of true positives divided by the number of true positives plus the number of false positives. So it's this number divided by the sum of the elements from this column. So this is the precision. The recall is also the number of true positives divided by the sum of elements on this row. So this is the recall. So precision tells you how precise is your model. So when it makes a prediction that a thing is a person, how sure are you that that object is actually a person? So that's the precision of the model. And recall refers to looks at the data set and looks, okay, you have this many persons, and how many were you able to label correctly from the entire data set. So this is recall. And actually the model, so imagine we have a linear model that separates the data sample. So yeah, so actually I should have animated some perhaps some linear model on top of this. So imagine that you just draw some separating border here between these two girls, let's say. So here you will get precision 1, so because everything that you predict is a person, but the recall will be very small. You will predict one person, but the other two will not be predicted or as people. So your recall will be 1 divided by 3. So if you move your separating line to the right, let's say about here, you get precision is 2 divided by the number of positively labeled examples that you predicted as positive, so 2 divided by 3, so your precision starts to decrease because you're also including this example, which is not a person. and but you increase your recall. So instead of 1 by 3, 1 divided by 3, your recall is you obtain 2 people, and you wrongly label another one. So if you move your move your line even more to the right, then you get, for example, a very low precision. So you would label 5 examples of people, and your precision will decrease because you'll have two false positives, but also your recall will be 100%. So as you move from the left to the right, you go from very high precision and low recall to very high recall and very low precision. So in the end, if you measure all these values in all possible locations, you get the precision recall curve, and you can also compute the area under these curves, and this area is called average precision. Okay, so yeah, this is the another important metrics that you can obtain. So this area, so imagine that this is a cube, right? A square. So if you cover this, the percentage that you cover the square is the average precision. So if you get 100% average precision, it means that your curve is actually it's actually as the square. So if it's lower, it means that you have lower performance. And you can also use this curve to achieve the desired trade-off between precision and recall. So for example, if you design a test for COVID, you have to think about the false positives and the false negatives, right? So you can label a person that it has COVID, but actually it doesn't, or you can also have you can also by mistake label a person that doesn't have doesn't have COVID, and you label as COVID, and one that has COVID and you label give the wrong label, it doesn't have COVID. So you have to think about these kind of errors and try to find the optimal trade-off with the minimum cost for the respective people. So in medicine, this is really an important thing to adjust the model to have the right bias towards false negative or false negative. Depends on what you want to achieve. Okay, so another way to look at this is to compute the true positive rate and the false positive rate. So actually the true positive rate is equivalent to precision, and the false positive rate is the number of false positives divided by the number of negative examples. So these are false positives and true negatives. So once again, these are complementary metrics. So if you move from left to the right as before, you will get different values. So again, if you try to improve precision, you will also increase the number of false positives. So ideally, you would want a model with 0 false positive rate and maximum true positive rate. So you want your curve to go around here. So anyway, considering these two metrics, once again you can build a curve, and this is called the receiver operating characteristic curve, and the area under this curve is called AUC. So this is called the area under the curve metric. So actually you have to remember that AUC refers to the ROC curve and not to the precision recall curve. For the precision recall curve, you have the average precision metric. Okay, then for a certain threshold, so once you fix your threshold, you can also try to express the precision recall in a single metric. So for example, if you want to compare different models, one can have higher precision and lower recall, and another one can have lower precision and higher recall. So which one to choose? Right, so in order to compare the models, we can use the F beta scores. So beta actually balances the weight between precision and recall. So it depends. For example, if you want to have higher precision, you can choose beta accordingly. But anyway, so if you want them to be equally weighted, beta will be 1. So the F1 score considers precision and recall with equal weights. So if you replace this with 1, this actually gets eliminated, and here we have 2. So the F1 score is 2 times precision times recall divided by precision plus recall. Yeah, and this is the most commonly used in practice. And it's just a single measure that combines both metrics, and you can be able to directly compare the models. Okay, so going to other types of evaluation methods, these are specific for specific tasks. So for example, in object detection, we use a criterion called intersection over union. So we just, for an object, we have the ground truth bounding box, and we have another bounding box that is our prediction, and we measure the error using the intersection over union criterion, or the Jaccard index. So this is the area in the intersection divided by the area in the union. So usually in object detection, a detection is correct if this measure is higher than 0.5. Okay, moving on to regression models. As I said before, we can use the mean squared error to estimate the error of these models, which is just the sum of the differences to the power of 2. And actually, this measure is not really very helpful. So for example, if you don't know the scale that you're working on, or your scale, for example, is different, so what I can do, for example, going to an example from last time, age estimation. So I want to estimate the age of people, and I want to address it as a regression problem. But you will see that in practice, you will obtain better results if actually you take the values 0 to, I don't know, 130, all possible value, and you scale them to the interval 0 and 1. So you will see that the optimization, you will obtain much better performance in this scale, but this is actually not due to just because you reduce the scale naturally and the MSE decreases. It's just that the optimization can be performed better in this because the data is normalized. Okay, so the thing is, if you use this reduced scale, you will see a very low MSE value. And if you think of the original scale, you will get much higher error rates, right? So given that the scale can be different, it's hard to. So if you see an MSE value, it doesn't tell you so much about how well the model performed, unless you try to compare with some I don't know, random prediction model or some other models, so that you can compare one with the other and see how their comparative results look like. So because of this, we can also use other models of estimating the errors of regression models. So one is, for example, how well does it align with assuming that you can take all the data samples from your test set. How well does it align with the order, the natural order given by the labels? So yeah, here I'm giving an example on image difficulty prediction. So we have an order of difficulty that is defined by humans, and our model predicts this difficulty, the difficulty in this order. Okay, so now if we look at the orders, the actual value that is predicted doesn't matter so much. So here, I don't know, this can even be in different scales. So this can be in the scale 0 to 1, and this can be in the scale, I don't know, 1 to 10. But it's not important, the scale and of the prediction of the actual label, but it's more important to achieve the same order. So if you try to see how well these rankings are aligned, you can use, for example, another measure that you can use is the Kendall tau. So Kendall tau is is a metric that counts the number of concordant and discordant pairs. So concordant pair, so I'll give you an example. So this is the mathematical formulation of what a concordant pair is, and this is a mathematical formulation of a discordant pair. So remember this formula is the number of concordant pairs minus the number of discordant pairs divided by the total number of pairs that is possible from your training dataset of n data samples. So yeah, one example. So yeah, you have to consider all the pairs in all the possible pairs of images. So we take the pair with the cat and this messy office. So we look. So in the first ranking, the ground truth one, we see that the cat appears before the messy office, and the same happens in our ranking. So the cat appears before. So this means that this is a concordant pair. Okay, so it means that in both cases, this image appears before this other image. So image I appears before image J. So this is what definition, this is this definition here. And here P is actually the number of elements in this set of concordant pairs, okay? And Q is the number of elements in the set of discordant pairs. So we have this example is the concordant pair, and this example is the discordant pair, okay? So we take another pair from our data set, the cat and the woman, and we see that here the cat is before the woman, and here the woman is before the cat. So this is not right, they are reversed. So this is considered a discordant pair. Okay, and now given that you know what a concordant and discordant pair is, my question is what is the value of Kendall tau? So you can try to answer, to give the final answer, or try to answer, to compute the components. Okay, so I'm sorry, I'm checking the answer right now. And I think, yeah, this is almost, I think it's almost the last slide for you guys. Okay, so probably I should keep this slide on so that you can see the pairs. So you actually, I think, try to consider all image pairs. So also note that the pairs have to be either concordant or discordant. So you can also try to compute only one of them, and then figure out the other from the total number of pairs. Okay, so going back to this slide. Okay, so I don't see any answers here. Okay, I think you're still computing, I hope. Is there anyone actually thinking? Okay, yeah, okay. I was just making sure so I don't switch down. I'm just trying to pick. I'm trying to do both in the same time, so just leave the... 8 divided by 10. No, it's not. You're close. Yeah, so Armand, you're close, but not. It's not actually the actual value. So we have here not, the answer of Lida is not right. So I'm still waiting for the right answer. So there is the total, the number of concordant, number of discordant pairs, and then the answer. Now the number of total pairs is not 25. It's actually smaller. So it's combinations of 5 taken as 2. I think for this small number you can also compute it. Yeah, okay, we have a good answer from Michna. Yeah, that's the right answer. It's 6 divided by 10. Yeah, so actually the fastest way to compute it is just to look for the here. I think most of the images or most of the pairs are aligned. So there are only 2 pairs that are not aligned. So it's this pair with the cat and the girl. So one pair that is discordant and another pair is this one with the office and the street scene. So another pair that is discordant. All the other pairs, so for example, if you take the cat, if you take the cat and I don't know, the street scene, they are aligned and so on. So we have 2 discordant pairs. We also have the total number of pairs. So there are 5 images. So the total number of pairs according to the formula here is 5 times 5 minus 1 is 4. So 5 times 4 is 20 divided by 2 is 10. So this is just combinations of 5 taken as 2. So yeah, this is the total number of pairs is 10. Okay, so if we have 2 discordant pairs, it means that the other 8 pairs are concordant. Okay, so P is 8 and Q is 2, and then when we compute Kendall tau, we have 8 minus 2 divided by 10, so this is 0.6. Yeah, so this gives us an intuition about how many pairs are aligned in the data set. Okay, so this was the last slide. Guys, if you still have questions, we can stay for 2-3 more minutes. Otherwise, we can end here. Once again, I'm sorry for starting the lecture later. Yeah, but it's amazing that I managed to finish it in 2 hours. I think 2 hours. Yeah, almost okay. Otherwise, yeah, if you don't have any other questions, we can just end the session. And YQ is 2. That's the number of discordant pairs. So we have 2 discordant pairs, the cat and the woman. So these are in a different order. And also the office and the street scene. So these are also reversed. So these are the only 2 pairs that are not in the same order in both. Otherwise, if you take, I don't know, the woman and the bike, they are concordant. I don't know, the woman and the street scene, they are also concordant. So they are always in the same order. So I mean, the woman is before the scene, the bike is before the office and the street scene, and so on. So the only 2 that are in reverse order are these 2 pair and this pair. Okay, so we have 2 discordant pairs, so Q is 2. Q is the number of discordant pairs. All the rest are concordant. Okay, yeah, so about k-fold cross-validation, indeed, so that's just to validate your model, right? And to fine-tune your hyperparameters. So once you find the right hyperparameters of your model and the right model and hypothesis class and so on, once you find that, you fix them, you train on the entire training data, and then you apply that model on the test set. So you are allowed to retrain the model one more time on the entire training data using all the faults, so using the entire training data, in order to make sure or in order just to have more data available and to obtain a better estimation. So it's nothing wrong with doing that. The only problem is you don't want to fine-tune the hyperparameters on the test data. So yeah, the final answer is just your final model is just a model that has to be trained one more time on top of all the training data. Of course, another option would be, so if you use this approach where you train your model on faults and then obtain a single model from that, that's called classifier bagging. It's also a technique that can be used to slightly improve accuracy, and it actually depends. In some situations it seems to help. So yeah, but I think that the straightforward way to do it is just to train the model on the entire data set. Yeah, so about the ground truth, actually we have a paper on that. So the ground truth is I think I cannot post a link on sorry, trying to look for Scholar. So it's this paper. So you just, if you search for this title, you will be able to find it, to find the PDF online, and you will see it's actually based on this paper. So actually the ground truth is based on, we ask people, do you see an object, like for example, is there a person in this image? And when you look at the image, we just measured the time that it takes people to look for the object. So if it takes a lot of time, the image is assumed to be more difficult. While in this image, if I ask you, is there a person in this image, you can immediately say yes. You don't have to look for it. And is there, I don't know. And also if I ask you about, because we also ask about objects that were not in the image. So for example, if I ask you, is there, I don't know, a bottle in this image, you might not see a bottle, but you still have to look for it and see if there is a bottle or not. As opposed to this image, if I ask, is there a bottle on this image, you immediately see that there is no bottle here, and the answer is no. So yeah, this is what's the ground truth difficulty that we used in this example. So if you want to read more about it, you can go and read this paper. Okay, are there any other questions that you would like me to answer? So now I see my answer is the last one, I think, with the paper title. I would have, let me just try, I tried before, I know, during the other class, but it didn't work. But I can try one more time to get the paper. Let's see if I can post a link here. Maybe not be possible. Only at this time it worked. Yeah, so just follow the link and you'll see the paper here. Yeah, you do not iterate on the test set to reduce the error, yeah. So if you mean by iteration, you mean adjusting the parameters, yeah. Yeah, so actually on the test set, you just do the final evaluation to get a good estimation of the empirical error of your model. And usually it's slightly lower than the validation error, because when you test a lot of models on the same validation set, you'll see you can overfit in hyperparameter space. So usually you can get a slightly higher validation error than the test one. Okay, so yeah, on the test set you no longer adjust your parameters. Okay, so I think there are no more questions. So thank you guys for participating. Once again, sorry for the delay, and see you next week at 6 o'clock. Okay, thank you.